learners, so in this particular session we will discuss about more examples of greedy techniques. So previously we have already seen greedy techniques algorithm like knapsack and coin exchange problem. So in this particular session we will be divulging deep into another topics like minimum cost spanning tree and how this particular algorithm is being implemented under greedy techniques, and what are how this is being implemented with the applicability of different algorithms. So minimum cost spanning tree, what is minimum cost spanning tree, how it is being implemented, what are the applications of minimum cost spanning tree will be discussed in this particular session. So again, it's a very simple concept. The definition is based on the graph theory. So before going deep into it, so you have to understand that the most used term in this will be something called a connected graph, undirected graph. So undirected means that there will be no arrow that will be given in a graph. So it means that if there are if there is an edge between two vertices, that is A and B, there will be no direction there. So firstly we will be following here undirected graph. Connected graph is that when the vertices are connected to each other, it is referred to as a connected graph. Means that any part of the vertices being that connected part will be referred to as a connected graph. Now, so here the definition follows as let G. So G is equal to V comma E. So what did it mean is that it is calling that a graph, and graph is equal to vertices and edges. So it means that a graph G contains a set of vertices and contains a set of edges. Now when it is containing a set of vertices and edges, it will be a undirected connected graph. A subgraph, now subgraph is represented here as a T, which again contains the vertices and edges as dash E dash of G, is a spanning tree. Now why here they are putting dash on E? Because the number of vertices will remain the same in a subgraph, which is referred to as a spanning tree, but the number of edges will be less as compared to the connected graph that is being called a G. Now it's called a spanning tree or G if and only if T has no cycles. It means that if you are able to form a cycle within a graph, then it is not a spanning tree. If there is no cycle and there are lesser edges as compared to the original graph, then it will be referred to as a spanning tree, minimum cost spanning tree. Now from this you have to understand points. First point is that you will be given a undirected connected graph which has n number of vertices, m number of edges. Now what is a spanning tree? Spanning tree is again a subset graph of this, which will have the same number of vertices, like n number of vertices, but it will not have m number of edges. It has a lesser edges as compared to the original graph. So a connected graph will always have a cycle. If a graph is connected from all sides, from all vertices, it will always have a cycle. So spanning tree condition is that spanning tree does not contain any kind of a cycle. So if it does not contain any kind of a cycle, so you have to reduce that particular part which is forming a cycle. So it means the edges will be lesser as compared to the original graph. Okay, so you will be given a graph, you have to obtain a spanning tree from the given graph. Now this graph will be a weighted graph. Weighted graph means every edge will be assigned a cost. Okay, so suppose there is a vertices A and B. Suppose there is a vertices A and B, and there is an edge between them. So if you write 2010 on the edge, it means that the cost from going from A to B is 10 or 20 or 30, something like this. Okay, so how many maximum, so there can be many spanning trees that will be satisfying the condition, but there will be only one minimum cost spanning tree. So what do I mean by this? So if in general a complete graph with n vertices has a total of n raised to power n minus 1, n minus 2 spanning trees. So what do I mean by this is that if you are given 4 n, so if the value of vertices is 4, so it means the total spanning tree is 4 raised to power 4 minus 2, which is 16. 4 into 4 is 16. So you can get 16 spanning tree. Out of these 16 spanning tree, there will be a spanning tree which have the minimum cost, because every spanning tree will have a edge, and on that edge the weight of that edge will be written. So that will be referred to as a cost. So a minimum cost spanning tree of a weighted connected graph is that spanning tree whose sum of length of its edges is minimum among all the possible spanning tree. Okay, so for example, consider the following weighted connected graph G that is shown in the figure 1. So you can see here there are 5 vertices, and it definitely contains a cycle. Okay, because it is a connected graph, so it will definitely contain a cycle, and every edge has a weight assigned to it. Now you have to make a spanning tree from figure 1. The spanning tree will have the same condition. All the vertices will be there, but it cannot form a cycle, and the vertices will be there, it cannot form a cycle, the number of edges will be lesser. Okay, so A, B, C, D are examples of spanning tree. Now if you check here, all these variations of spanning tree do not contain any kind of a cycle. Okay, so you can go from A to C, C to D, D to E. In the first variation A, you can go from A to C, C to D, D to E, and there is no cycle because the edge between B and C is not there, so it means it cannot form a cycle. Similarly check for B, similarly check for C, similarly check for D. Calculate the weight, calculate the cost that is being associated with every variations. So with A the cost is 41, with B the cost is 37, with C the cost is 38, with D the cost is 34. If you check it, the minimum out of these is actually 34, because this is not actually the minimum cost spanning tree, because we have not drawn every combinations of it, because there are 5 vertices. So what do I mean by this? There are total 5 raised to power 5 minus 2 spanning trees are possible, that is 5 raised to power 3, meaning 5 5s are 25, 25 5 the 125 spanning trees are possible, but we have only drawn only here 4 spanning trees. But in this 4 spanning tree, the minimum cost spanning tree is the spanning tree which has 34 cost, but it may not be the minimum cost spanning tree because we have not tried 125 combination to check the cost. Okay, so minimum cost spanning tree will be only 1, but spanning tree can be an n raised to power n minus 2. Okay, now what are the applications of spanning tree, why we are using it? So spanning trees are basically used for designing efficient networks. So what do I mean by this? It used in networking so widely because in routing algorithms it is also being used. So we design a network. If you simply want to design a network in which a group of individuals who are separated by varying distances wish to be connected together in a telephone network. So this problem can be converted to a graph problem in which nodes are telephones, undirected edges are potential links. The goal is to pick enough of these edges that the nodes are connected, enough of these edges that the nodes are connected. Each link, that link will be called as an edge, also have a maintenance cost. So reflected in that edge's weight is this. So now the question is that which is the cheapest possible network? So an answer to that question will be the minimum cost spanning tree. In other words, that it is also used for designing efficient routing algorithm, because most of the time you have to you have to find the shortest path that is being available, and if it is forming a kind of cycle, then the path or then the packet can lost in an infinite loop. So that we definitely do not want. Okay, so the applications of spanning tree are basically in building efficient routing algorithms and basically in designing an efficient network. Now, so there are two ways to find out the minimum cost spanning tree. First way is referred to as the Crucial algorithm. Another way is referred to as the Prim's algorithm. So again, these two algorithms are based on greedy approaches. Greedy approaches selects the edges one by one, some order. The next edge is to choose according to some optimization criteria. The simplest such criteria will be to choose an angle u and v that results in a minimum increase in the sum of cost. So both of the algorithm establishes the same thing, that they will be finding out the minimum cost spanning tree rather than building all the spanning tree. Like in the previous example, there are 5 vertices that is being available. So we will not be building like 125 spanning trees and calculating the cost of 125 spanning tree, and whichever cost is less will include that, say that this is the minimum cost spanning tree. It will take a lot of time. So for that we have a direct algorithm that existent, that is Crucial algorithm and a Prim's algorithm. So what they do is that they will directly build the minimum cost spanning tree by following greedy technique or greedy approach. So the steps are very simple. First, we will build a set A of edges that is always the subset of some minimum cost spanning tree. So you are taking a look at it, every problem that is being given. Suppose we are given a coin exchange problem previously, where we are also taking the input from a candidate set into a solution set, and that solution set is also a subset of the candidate set. Similarly here also, if you are taking here that you will be given already given a graph there, and based on that graph here you will be adding the edges into the graph in the solution set. So again, whatever solution you are getting is the subset of the candidate set, that is C. So here also that you will be given us a graph with the vertices and edges, and whatever you are getting is a subset of that graph. Okay. So initially the A set will be empty because it will contain no edge. Now at each step one edge will be determined, and such that if that edge has been called a safe edge, meaning it follows a certain criteria, then that particular edge will be added to the set A. And then another is that will always add something called a safe edge. A safe edge will be that edge which will follow the criteria that this is the minimum cost of the edge that is being detected till now. Another thing is determination. How will you stop? So you will stop when you are able to add as many edges as you can and you are not able to get any kind of a cycle, and when all the safe edges are being added. So simply, if you can say that simply the safe edges are being added, means safe edge is a edge safe edge is a edge in which by adding the safe edge the cycle in the graph is not formed. So if you are able to add all the safe edges, then you can stop adding another edge. So this will be the stopping condition in order to build a minimum cost spanning tree. So a generic minimum cost spanning tree will the algorithm will be, you will be given a graph and you will be given W, which will be the weight of that graph of a certain. Now graph will contain a vertices and edges. So you will, again, the algorithm says that you will start with the set A, which is empty. Now while A is not a complete spanning tree, you will keep on doing these steps. The first step is that you have to find an edge which is safe for A. You will if this is safe, it will be added by taking a union of it. You will add and you will continue doing that until you are not you have added all the safe edges. Now in the end you will return the value of A. So the Crucial algorithm is again implementation of minimum cost spanning tree. So Crucial and Prim's algorithm established the same concept but in a different way. Okay, so how it is working? So I'll discuss each and every step one by one. So firstly, Crucial algorithm is following these steps. Firstly, it will be taking the graph, weighted graph, and then it will first examine the edges of the graph in order of their increasing weight. So it will arrange the edges in increasing weights. So what do I mean by this? That the starting edges will have the minimum weight. Now then we select a edge with the minimum weight and check whether its endpoints belong to the same component or a different component. If they belong to a different component, then we add it to the set A. Otherwise it is rejected because it creates a cycle. So I'll show you what do I mean by this. And the algorithm stops when only one connected component remains. Okay, so all the edges are being added, only component is being remaining. So now the Crucial algorithm is given as, if you see this this one. So firstly, the Crucial algorithm stored the edges in an increasing weight. Then it will start the set with the 5 because it does not contain any edge in the starting. So for each vertex that belongs to the graph, it will call a function make set. Now each edge that belongs, each edge u and v which belongs to the edges that are in the original graph taken in the increasing order. So for that you just check find set. If find set u is not equal to find set v, then you can simply add it to the graph. Otherwise it's simply add it to the graph and merge u and v. Otherwise you can directly ignore that and you can simply go to the another edge part. So there are three functions here. First is make set, another is find set and find set u and find set v, another is that merge. Okay, so now, so what this algorithm represent is that the make set at line 3 and 4th function says that for all the vertices of G for a graph with n vertices, it makes a n component of disjoint set. So make set will only contain a disjoint set in line from line 5 to 8. So what we are doing is that we are adding the minimum weight to the set A if and only if it join two nodes which belongs to different components. So that is why it says find set u is not equal to find set v. If they are equal, then you are not adding it. If they are not equal only, then you are adding it, because then it contains that it contributes to a different vertices. Okay. So if an edge A is added to the component containing its endpoint are merged into a single component. Okay. So in this example, we will see that the first thing that you have to do is the algorithm, that you have to arrange the weights according to the increasing order. So you have already in this particular example we have already arranged. So the edges are 1, 2, 3, 4, and the weights are 2, 3, 4, 4, 5, 5, 5, 6, 7, and 8, 8, 9. So firstly, you will start with the inclusion of the minimum cost into the edge. That will become your the first edge that held to be added in the algorithm is 1, 2. So you add 1, 2 in the set. By adding 1, 2, there is no kind of a cycle is being formed. So the next minimum cost is 3 that you are getting, that is 2, 3. So by adding 2, 3, again the 2, 3 edge, you are not getting any kind of a cycle. So you can simply add it. So by adding the next cost is minimum cost is 4. By adding 4, 5, again you are not getting any cycle. You can simply add it. Another minimum cost is 4 by 6, 7. So by adding 6, 7, again you are not getting any cycle. So you can simply add it. Another minimum cost is 5, that is of 1, 4. By adding 1, 4, again you are not getting any kind of a cycle. So you can add it. So the next minimum cost that you are getting is 2, 5 of vertices 2, 5, 5. But by adding 2, 5 into the set, you are getting a cycle. So it means you cannot add this particular part. So what do I mean by this is that if you include 2, 5 in the edge, the cycle between 1, 2, 2, 5, 5, 4 and 4, 1 will be formed. So minimum cost spanning tree do not contain any kind of a cycle. So you cannot add 2, 5 here. So similarly, you cannot add 2, 5 because it creates a cycle. So another part is that move on to the next one. The next one is 4, 7 with a minimum cost of 5. So can it be added? Yeah, because the inclusion of 4, 7 does not contribute to a cycle. So you can simply add it. Okay. So if you check it, the number of edges here are 1, 2, 3, 4, 5, 6. Okay. So it means that 6 edges of 7 vertices are being added. So the because if you include any more edge, it will tend to form a cycle. So after 4, 3, if after 4, 7, if you add 3, 5, okay. So if you add 3, 5, it will again form a cycle. If you add 2, 4, 2, 4 will again form a cycle. If you add 3, 6, 3, 6 will not form a cycle, but the number of edges that you need to calculate is n minus 1. So if there are vertices n, the number of edges in a minimum cost spanning tree will be n minus 1. So here the number of vertices are 7 and the edges we have already calculated as 6, and you can simply add the cost. The minimum cost spanning tree has a cost of 23. So similarly, the Prim's algorithm is based on the same lines here. You have to perform the same steps, but it is a bit different than Kruskal algorithm, because Kruskal algorithm is based on the increasing order in which the first part is set. So you will arrange the minimum cost in the increasing order, but it is different. Prim's algorithm is different from Kruskal in that way. So I'll tell you. So firstly, it will start from anything. It will start from any vertices. Initially, you will get a set of nodes contain single arbitrary node. Starting vertex will be random, and then the set T of edge will be empty. So at each step, Prim's algorithm looks for the shortest possible edge which is being connected to it. Okay. So I'll show you in the example here, and this particular step will be performed until you will get the solution. So look for this particular, the problem is same, now the solution works differently here. Okay. So suppose I am starting with the edge 1 2. You can start with any edge, but I'm starting with 1 2 because initially you can start with any edge. So in the Crucial algorithm you always have to start with the minimum cost, but here you can start from any edge. I'm starting from the vertex 1. So this vertex 1 has two edges that is connected to it, that is 2 and 5. So you will consider the minimum out of these two. So by adding, which is the minimum here, the minimum cost is 2, so you will add 1 2 edge here. Okay, so I have selected the first vertices as 1, and with this vertices 2 edges are connected, that have a cost of 5 and 2. Select the minimum cost. Now by adding the edge 2, you will also get another vertices, that is 2. Now check with the vertices 2, there are 1 2 3 edges that is being connected, that is 7 5 3, and also include the edges from the first vertices, that is 2 and 5. So the minimum edge out of these is 3, so you include the 3 there. Okay, so when you include the 3, again you have to calculate all the connected edge which has the minimum path. Okay, so 1 2 3, meaning these 3 components are connected to another vertices, and you have to select that edge that has a minimum cost. So out of these, 1 4 has the minimum cost, that is 5, because if you look at 2 4 has a 7 cost, 2 5 also have a 5 cost, 3 5 have a cost of 6, 3 6 have a cost of 8. So there are 2 cost 5 that is being there, that is 1 and 4, and 2 or 4 5. So you can either select either of them, there is no problem. Okay, so you select, if I am selecting here 1 4, and then you proceed further. So again calculate the minimum out of these connected components, that is 1 2 3 and 4. So out of this you will again get the minimum edge, which is 4, because you will get 5 5 and 4, and 4 will be the minimum out of this, and you will add 4 and 5, and so on and so forth. So you will keep on going until you get the number of edges, which is n minus 1. So this is how you build a minimum cost spanning tree in case of Prim's algorithm. So Prim's algorithm is a bit different of Crucial, because Crucial is based on the number of posts in arranged in a increasing order, and you have to add that cost, which does not form a cycle. But here is that in Prim's algorithm you have to depend upon the number of vertices, and have to check the number of edges which is connected to each vertices, and you have to select the minimum vertices. Okay, so in this session we have seen the different applications of minimum cost spanning tree, as well as we have seen the implementation of minimum cost spanning tree in terms of algorithms, Prim's and Crucial. So in the next session we will see another technique, another different technique from greedy, that is divide and conquer technique. So here your greedy approaches we have seen till now is, first greedy approach we have seen with the help of a coin exchange problem, then we have seen knapsack problem, then we have seen minimum cost spanning tree. So we have done many approaches, there are also many more. So in the next one we will be discussing about divide and conquer approach. Thank you.